So, welcome everybody. My name is Maciej Suliński. I'm a senior AI programmer at 11 Meet Studios, and I'm here today to talk to you a bit about our approach to game AI and some of the challenges that we have faced while working on an unannounced project. And because the project is unannounced, unfortunately, the presentation will be a bit dry and high level, so bear with me. And before I continue with the actual topics, just wanted to acknowledge my teammates and their contribution. Everything that I'll be talking about later today, we all work very closely together on. So the few challenges I decided to highlight, of many that they were, today are following: having to support multiple enemy archetypes and roles in our game, and how we were able to leverage a true AI composition workflow for that. Enabling designer control and how we provided our designers with a scripting solution that didn't disrupt the actual systemic decision logic. And a challenge of AI debuggability and how we created a custom runtime AI debugger that leveraged our architecture and significantly improved our workflow. So a quick background on the project itself. It's a single-player stealth action game, third person, built by approximately 40 people, so you get the scope of things. Development actually started on Unreal 4, so we didn't have access to some of the newer stuff that 5 ships with, for AI or otherwise. We didn't also have any existing tech stack from previous projects to lean on, so it was a clean slate, for better or worse. And lastly, the scope and team composition demanded empowering designers. That's not something you should strive for either way, but the overall design direction skewed more towards handcrafted approach to encounters, and we had many special gameplay sections to handle that were either born out of level design needs or often narrative purposes. So initially, when we started on the project, our kind of guiding principle was to avoid all kinds of one-size-fits-all solutions. So just because Unreal 4 ships with behavior trees, we didn't want to use that for everything and anything AI-related in our project. Because while behavior trees, when appropriately applied, can be effective, they have their shortcomings in other areas. And if you're using them for high-level decision-making, they can easily explode in complexity and weird workarounds. So with that in mind, we are careful to implement any atomic actions of our NPCs as either AI tasks or abilities, and I'm referring to the gameplay ability system. We have our own version of it, but conceptually it's the same, as sort of building blocks for our behaviors, all to ensure reusability of those actions and integration flexibility. So whatever system we would end up with in the end, it would boil down to how do we actually schedule those actions. And also to be sure that we can execute them outside of any AI systems so that we can easily test them or use them in scripting, that kind of stuff. And the thing that we quickly put together to get things running and unblock other teammates was to make a simple state machine-driven decision layer. We actually use the logic driver plugin. So if you're not aware, it's quite robust state machine implementation with visual editing that's quite extensible and so on. And we customize it to our needs. And that high-level decision maker, the state machine, would essentially request execution of behavior trees. And those behavior trees were our action sequencers. And we had also small another component which was separate from those two. We called it reaction sequencer. At that time, it was specifically to handle hit reactions, and it was simple rules-based solution. So we had entries for every hit reaction with activation conditions. We selected those with the highest priority that could be activated. It would interrupt the state machine and behavior tree, and after the reaction has ended, those two would be resumed. And in the beginning, it was fine. There were some issues that we were anticipating, but largely those challenges that I mentioned and some other stuff, we needed something better and more flexible for our needs, especially since the state machine to support all those different variations and archetypes grew sort of too abstract to our needs. And there was significant mental overhead with different subgraphs. And also we had dynamic states that referenced other state machine assets to handle those different variations, and it was just not pleasant to work with at all. So while we are planning how we can upgrade that and address those issues, possibly modify the state machine somehow to be more dynamic, we stumbled upon a very, for us, crucial and inspirational online presentation. Some of you, if you are interested in game AI, maybe probably already have seen it. So you might know where it's going to. If not, I'm glad to shed some light on this because I really feel it's a very good approach. So approximately, I think 2 years ago, industry veteran Bobby Angelov has shared his presentation online on his preferred solution to AI decision making. And that was pivotal to our direction moving forward. The concept that were discussed there very much aligned with our direction and needs of the project. And also we saw a very clear upgrade path that we could do very quickly and in a non-destructive way without disrupting the whole production process of the title. And we've adopted it to quite a great success internally. And the way I see it is essentially saved us a whole production cycle to arrive at similar conclusions, possibly, with probably implementation halfway there. I will attempt to give you like a rundown of the essential stuff and how we kind of use them and implemented some of those. But I would highly encourage you, if you don't know what I'm talking about, to go to the source and look it up. It's very, very insightful. So the essence of it, when talking about the decision layer, is dividing it into 2 distinct problems. What are all the things that can be done by an NPC or AI, and which one of those things should be done, of those that are possible? And there are different separate mechanisms that answer those questions and solve those issues. And this essentially has split our previous decision layer into 2 separate stages. And some of the issues that we were battling at the time, we didn't realize that actually stemmed from the fact that both of those questions were responsibility of our one state machine, which also bound by its layout, generated all those issues that we are having. So the objective generation, that's how we call it in our project. Bobby referred to it as goal generation. We call it objective because too many people initially, internally, made a connection that it's a planner, which is it not. So yeah, power of language. Objective generation defines what is possible to do, and it doesn't take any actual part in the behavior selection process. An objective is just an actionable aggregate information, a piece of data about the game state that is used later by the behavior selection. So it might be something like an enemy that can be fought, a sound that can be investigated, or a patrol path that can be followed. And generators are objects, essentially, that are responsible for creating, updating, or removing those objectives from the available set. And the generation rules are based on, quite often, the knowledge of the AI or the world state. So it can be usually things from perception, in our case, like actors that are seen, or any heard stimuli, that sort of stuff, health amount. And the implementation of generation rules is very specific to any given generator or objective. So there isn't any systemic, generic way that they are managed. So it's case by case, depending on the actual use case. It's very explicit implementation-wise. So a very quick example to kind of visualize how they are generated. Let's say we have an enemy with a patrol path. We might have a generation rule that says if there is any nearby patrol path that is unclaimed, that is something you can follow. So an objective will be created with an entry about the data of the actual patrol that can be followed. There might be an explosion nearby that is heard by an enemy. Then that would be another rule that specifies, okay, there is a sound that you've heard, it's an explosion, that is something you can react to. An objective would be generated for that. Then footsteps might be heard, and that same objective with the same generator would update the existing reaction objective with new entry. So it lists all the possibilities that can be attempted by NPC to act upon. And also, there might be another rule that specifies that footsteps are actually something that can be investigated. And then let's say player pops up, there is a line of sight. There might be a rule that specifies that it's something that you can engage in combat. It's a valid combat target with all the information needed. So here is an example of what contents might be in such objective. Here on the left is our objective. It's simply a U object. It contains a list of different entries. This is a react to sound objective. And here is data that whatever is needed for either behavior selection later on or execution of it. It might be something obvious like location of the sound, a gameplay tag that specifies its type, or maybe something more tailored to your needs. For example, whether that sound location was in view when first it was heard. And here is an example of a very simple generation of a patrol objective. Essentially, we gather all available patrols. Our patrols can be claimed and unclaimed, so any that's nearby that's unclaimed yet. If there are any, then we would create or update existing objective. Otherwise, we would either invalidate if there is one already or just do nothing. And implementation-wise, it was very straightforward. We essentially had a dedicated component for that, where we had a set of generators available in that instance. And it would just, anytime we would update the generation, we would essentially iterate over all of those, invoke their update functions where those rules were implemented. And in that component, we would keep a list of all objectives. And also, those generators can have settings. Like with patrols, for example, we could specify specific tag query to filter out different types of patrols that might be usable only by specific archetypes or something like that. Now, the behavior in this concept is essentially the action sequencer. So like previously, we used behavior trees with a couple more things. So the actual action sequencing that is done by a behavior can be implemented in whatever way you would like. Because we had all that previous implementation and we wanted that flexibility of having different precise solutions to problems that excelled at specific types of situations, we've supported behavior trees, state machines, blueprints, and code for our behavior logic. And we essentially just had a instance wrapper for all those types with sometimes additional settings, like, for example, behavior trees. We exposed whether we want to run them in a single run mode or a looped mode, which is the default when you run them via the AI controller. Bless you. And here is an example of part of the non-destructive upgrade thing that we could do, which essentially we would pluck out existing state of a behavior from the old high-level state machine and use it as our logic for sequencing. This is an example of a searching behavior that we had at one point from that our customized logic driver state machine. And it was just much more sensible to use state machine for this particular behavior because we had something we called search points in our project, which were either smart objects or patrols that could be marked by a designer with a gameplay tag of a search point. And if any of those were available, they would be used instead of just roaming around a search area. So this was our solution for kind of directed searching movement that was very design-driven. Behavior selection. It's pretty simple. It's based on three things. First of all, activation preconditions. That's primarily based on those objectives I mentioned before, but not exclusively. Here is an example from our melee attack at one point, just a basic one. What we do is essentially just check if there is any combat objective available, and if so, there is an additional check if any of the targets from that objective have a straight navigation line from the enemy to the player. If so, this can be activated, otherwise it fails and it won't be selected. Behaviors also have cooldowns, which is kind of obvious, and also a dynamic scoring. So behaviors essentially have activation function, a cooldown, and a function for a dynamic score, which this scoring is also very case by case. I will later give you some idea of how it can be used. And the selection process itself is performed on a list of behaviors in 2 steps. First of all, we filter out any behaviors that have failure preconditions, and then we select the remaining ones with the highest score. Important to note that there is no needed order in this, so the order of evaluation doesn't really matter, which will be important also later on. So the previous example, how possible behavior selection could work out. Let's say we have this set of behaviors, and we iterate over all of them and see if they can be activated. So can searching be activated? Well, there is no objective for that. There is nothing to be searched for, so we disregard that. Dodging as well, there is nothing to dodge. It goes away. There is an objective to patrol, so this stays. We can react to sound. We can investigate something. Healing, let's say that the precondition for healing might not be objective-based, because you don't have to. It might just directly communicate with a component, like health component on a character. And in this instance, the NPC is healthy. We have a combat target. There is a straight navigation line, so melee attack stays. We haven't received any damage, so it goes away. And also there are no nearby allies. We don't have objective for that, so it's filtered out. And then we run for the remaining behaviors a scoring function and select the one with the highest score. And worth mentioning is that this example is not too far off with our day-to-day iterating with designers, where essentially we just specify maybe a design didn't account for a specific situation in the game, like, hey, here are all the possible things that can be done. This is currently selected. Is it okay? Should it be adjusted? And if so, what do you expect to happen on the screen, essentially? And we don't have to dive into more technicalities of any sort of implementation. It's a very natural way of translating that to implementation. Another important concept from Bobby's presentation are behavior groups. They essentially are reusable preconditions. They can contain other behaviors and other subgroups. And if a group fails its precondition, then evaluation of all its contents just doesn't happen. So it can act like an early out. This is from our custom editor, and one thing of note, again, there isn't any root here. This is just visualization that we went with, that kind of list view, because it was just very quick to do in Unreal. But yeah, order here in evaluation is irrelevant. And in this example, we have a combat group, an encircling behavior that it contains, a ranged subgroup, and a ranged attack that's contained in that subgroup. And those behavior groups can be very effective in two ways mainly. One is to just manage the available behavior set in a sensible way. And the other one is to avoid potentially performance-intensive checks that you might have in your activation rules. So let's say that the attack, the ranged attack might have some collision queries for line of sight and other stuff, and you don't want that to be evaluated every time that this behavior might be considered. So in that regard, you might create a combat group that only checks for a combat objective. So anything, if combat isn't available, any of those things would just not evaluate. And also you might have a ranged subgroup that's maybe checks for ammunition and that kind of stuff. The next thing are critical priority behaviors, which is just a collection of behaviors that are evaluated every frame, and they're meant to handle those behaviors that should be very responsive, that should interrupt currently active behavior. Things like hit reactions, but not exclusively. And here is an example. We have two buckets. One is for critical behaviors. The other one is for normal behaviors. And if any critical can be selected, it would interrupt the normal one, or another critical behavior that's of a lower score, and that can be interrupted. And the last thing from that high overview of this concept is that all of those things from previous, like the lack of static prioritization in the evaluation process, allow us to very easily add and remove behaviors at runtime. Behaviors themselves have a unique name within their owner context, so an NPC that has them. It's just a group path, essentially, and behavior name. So there cannot be a behavior with the same name as another one on the same in the same level. So here, for example, we have from our debugger a combat group, melee subgroup, and a quick melee attack, and that would be the unique name of that specific behavior. That can be, by using this unique name, removed or added again. And you can then package those requests of adding and removing to allow for that true composition workflow I mentioned in the beginning. So, going back to those challenges that I've mentioned before. The way we could now essentially make our enemies is by using those modifications, those requests that are packaged. We've named this behavior modifiers, so those are those elements that you can see here, which are just packages of adding and removing a behavior. And because it's stack-based, it's evaluated from the first to the last element, and it essentially flattens all the requests to get you the final set of available behaviors. Maybe if there's multiple requests to add and remove the same behavior to get the final result. And also at runtime, anytime a modifier is applied or removed, final set would be recalculated that way. And also implementation-wise, again, something really fancy. We have a dedicated component that's responsible for the behavior selection, and it contains a stack of those behavior modifiers that works on during the behavior selection. And here is an example of a modifier that we've made at one point for a group leader role for our needs. So it adds a critical reaction for a dead follower. It also removes a whole group of investigation, because if you specify just a group name, you can get rid of all the things that were included in it. And also some reaction to investigation of a follower and a command to tell someone to investigate. This was done because our designers requested for that role that a group leader should never investigate on its own, and instead it should command its followers to do that for him. So this way, we were very flexible with how we can form actual groups and specify who is a group leader and handle situations where, well, if all followers are eliminated for whatever reason, then we could just remove that modifier from a glue reader, and it would turn into a normal NPC that can investigate and all the stuff. Additionally, those modifiers also have onApply and onRemove events. If you need to adjust any state, it can be as simple as those here from our example, where we just apply a leader tag from that modifier. But it can be so much more. I mean, you can imagine, for example, a Berserker modifier, and you would want to possibly change the team of that character so that even allies are considered as hostile targets. And if a Berserking effect would run out, you would simply just remove that modifier and the NPC would go back to normal. So it has many uses in our project, but one of which was pretty useful for us, is what we called behavior zones. Essentially volumes that could be assigned, an NPC could be assigned to that volume and unassigned by a designer at runtime or at editor time, and it would simply apply a modifier when an NPC would be assigned to it and remove when unassigned. Originally, it actually started as a form of leashing that our designers requested to have to constrain movement in certain areas of a level. And it was actually useful for some other stuff as well. For the leashing itself, it was very flexible to us to control how strong the actual leashing should be with the dynamic scoring and preconditions. I will show an example just in a second. But it also proved to be useful for other stuff, which essentially allowed our designers to assign spatial roles. For example, a guardsman that would apply a guardsman modifier in a specific area, or even something we didn't use but toyed around with, a behavior zone that would follow the player, and that would assign enemies like a charger or engager behavior modifier. So, a quick example. We have an enemy outside of a leashing zone that is assigned to. We have a generation rule that simply looks for all assigned behavior zones and checks if the enemy is outside of it or not. In this example, it is, so an objective is created, and let's say there are footsteps and a player that can be engaged with. And in our case, our designers didn't want that leashing to be very strong and feel gamey, so we had a very high level of control of how to manipulate that and iterate with them. For brevity's sake, let's say those are only behaviors available in this example. And in this scenario, let's say designer asked us that the enemy shouldn't investigate footsteps or any noise while outside of a leashing zone, but if there is a player nearby, they should be able to engage in combat if it's not too far away from the leashing zone, so it doesn't stand there and just do nothing and looks like a bug. So in this case, a chase behavior in its preconditions might simply check if there is a return to zone objective. If that's the case, then I cannot be activated. And same goes for investigation. So that's done. And for the return to zone, we could specify in its scoring function, for example, a threshold for a designer that could be set up, like exposed to a config file, to specify at what threshold of the distance after it's exceeded, the score should be much higher, let's say a 1, or something like if the enemy would be very near the leashing zone, of a very low value. So you would run the scoring and just select, again, the one with the highest one. Another example of how flexible all this is, if a designer would like to have a very strong leashing zone, then you could go and let's say designer would say that they don't want the investigation or chasing to ever actually allow the enemy to leave the zone. In that case, the investigation and chasing could have in its preconditions simply check for all the assigned zones that are available to that enemy and specify that if the target of investigation or the chasing is outside of that zone, then it cannot be activated. And that explicitly is very flexible and easy to work with, at least in our cases. So, another thing that I mentioned of the challenges was the designer control and how we were able to give them a solution to influence our NPCs without disrupting the decision logic. And really, it boils down to of creating specific objectives. We have made something we called AI commands. There was actually a dedicated subsystem that would manage those. And if you would issue a command, that possibly would be available to other NPCs. And again, there would be a generator with a rule that if there's any command available to you, here's an objective, you can use that, but you don't have to. And because it's evaluated as like with the leashing zones for like normal decision-making process, again, we had a very high level of control of when those commands should be actually used, when they should be ignored, and so on. Also, our commands supported a few other bells and whistles. We could actually spawn command volumes in a certain location with a certain radius. Also with a tag query to filter out allowed NPCs that can use those. And there also was possibility of using of many NPCs using the same command volume when it was issued. And that was our main way of enabling designers to actually script those NPCs without disrupting the decision logic. So many cases that we had, because of some of the narrative-driven approach to those encounters, was that designer would like to have maybe specific opening to an encounter in gameplay, and they would command an NPC to maybe investigate specific targets on a level or move somewhere. And we didn't want to force our designers to be AI programmers. They had enough work as it is. So that way, if, for example, there would be an investigation command, but enemy would fail stealth or try to run over to the enemy, the other behaviors of the combat and so on would take over easily. And there were, depending on the command, there would be back and forth with designers of how they would expect it to be treated in gameplay. And also, I won't dive into it too much today because it's kind of a broader topic, but it was also an effective tool in coordinating group behaviors for us, although we use it sparingly, because usually there are easier ways to achieve those things. But for example, for that group leader, his behavior of issuing a command actually issued that AI command. And in that example, it was very useful as we wanted to have a very clear cause and effect visually, as it was something that usually player could observe for a quite long amount of time. And having those commands was very easy. Additionally, like with the scripting, the nature of those commands proved in a way to handle all other edge cases that sometimes we weren't aware of, but were handled because of them being part of the decision process of all the other selection mechanisms. And the debuggability and how it improved our workflow. Well, this architecture itself lends itself to building quite easily robust tools. And before, with our old solution, we had few issues with those subgraphs that I mentioned and the multiple assets that were referenced, and also the nature of a state machine and how it's bound by its layout didn't feel very debuggable the way we wanted to, at runtime specifically. So at that time, our most effective tool was the visual logger. And it's still to this day, it's crucial part of our QA process. Like anytime we have any bug AI related, we get from our QA people a visual log that we can sift through, and we don't have to actually reproduce these steps if they are pretty hard to reproduce. But also Visual Logger wasn't designed to be a runtime solution for debugging, and it was sometimes cumbersome if we wanted to quickly experiment and iterate on stuff, to do a playthrough, record it, stop it, go through the logger, repeat that. It was breaking our flow, and we wanted to improve upon that. So we've made this. This is my daily command center. Only a part of it, because there are many other sections. I had to chop it in different slides. But it essentially gives us a very clear view of everything that's happening with our AI. And it's all thanks to just the simplicity and how decoupled all these steps are. So here, for example, you can see the behavior selection, the actual information about the behavior that is currently running, and also a timeline with all the stuff that were happening, like deactivation and activation, when it has happened, why, and so on. We've implemented that with the Unreal Net GUI plugin, which you can find on GitHub. And actually in-house, this is our main solution for many runtime debugging tools. You don't have to use it for debugging only. You can actually also make in-editor tools, but that's our main use case for it. And yeah, here is an example also that you can see that we show all the currently available objectives and contents of those objectives. So we have like a very bird's eye view on all the things that are happening. Also, we have a section for our behavior modifiers where we can see currently applied ones, and also can apply any other modifier that is found in our project. And it was very useful for A/B testing or just iterating on stuff, or sometimes reproducing certain interactions. And also we have a view to see what those modifiers actually do and how they affect the stack of and the final result of our behaviors. So here is the behavior selection window. Pretty simple, similar to our Unreal editor that we customized. Again, it might give a wrong impression, but there is no root structure here. This was just very easy to implement. There are better ways and more efficient screen space-wise to do that, but it was just something to be done very quickly for us. So here you can see that all the things that are grayed out failed their activation precondition, or their group has failed it. The things with white label can be activated, and the things in yellow have been actually selected, and there are also scores and sometimes even a cooldown. Also, inspired by the visual logger, we've added a timeline, both visual and kind of text-based, where we could see and sift through it in runtime of everything that has happened behavior-wise. We could see also the lifetime of objectives, those slim bars, and a couple of other gameplay things for our needs. The x-axis was the game time, and the y-axis was enemy awareness, which was an important value in our project. It was essentially a measurement of how aware of danger enemy is. To control states like, it essentially had values from 0 to 2 of being relaxed in 0, being alerted in 1, and hostile in 2. And that was used often in many different behavior selections. So we had that graph here, that blue thing, and that signified that. And there were also other things like perception events drawn and that kind of stuff. And also our text-like version of it, where we had more information about why something has been interrupted or failed, information about with any of those timestamps, what objectives were available and so on. And it was very quick and easy to find issues or unaccounted situations and address those that way. So, in summary, some of our key takeaways, at least, is I would definitely recommend to have a decision space layer, even if you wouldn't go with all the other things that I have mentioned. Having that separate and having that answer to what can be done greatly simplifies many other things. Maybe I didn't highlight it enough today, but by the virtue of those objectives alone, integrating AI mechanics with different gameplay systems is much, much easier, because the default answer usually is, okay, how do we make an objective out of it so that it can be used? Another takeaway is to invest in tools. This is kind of my own pet peeve, where I really believe that enabling people to efficiently work with your feature can be just as important as achieving your functional goals. And I can stress enough how useful that debugger has been for not only us on the AI team, but also QA, designers, and everyone involved. It was a game changer for us. And lastly, I truly believe that Bobby's concept is great. And you heard my testimony, I suppose, and I would encourage you to go and watch the videos. Thank you.